Hello everyone. My name is Gauri. I'm your MC for this session today. Welcome to the TMLS 2021 Annual Conference and Expo session with George Seif. The topic is Cost Reduction Methods for Machine Learning in Production. So, a little bit about George. George is a machine learning engineer with expertise in bringing machine learning technologies to production at scale. In the past, he worked at Indus.ai, that was acquired by Procore Technologies, designing and building a machine learning system for applying computer vision to construction analytics. He currently works at Altair Engineering, where he is working on building an open, extensible, scalable, cloud-agnostic MLOps platform to make taking ML to production faster and easier. So without further ado, I'm going to welcome George to this session. Welcome, George.
Thank you, Gauri. Thanks for the intro. Hello, everyone. I hope you're having all a wonderful day so far, and I hope to make it a little bit more exciting as well, hopefully, with this presentation. I'm going to start sharing my screen here in just a moment. Okay, yep. And today we're going to be talking about cost reduction methods for machine learning in production. And what I want to start off with is really setting the stage here. And that's with this pretty enormous number, $50 billion. What this is the worldwide projected market size for 2021 for machine learning, otherwise kind of known to the public as artificial intelligence. Now, you'll hear different numbers here and there. Sometimes you'll hear $60 billion, $70 billion, or whatever it is. But kind of point being is that this is a huge market and there's a lot of business opportunity. And it's a very exciting time to be in this space. And it's only growing. There's a lot of projections for 5 years down the line, like 2026, that are saying, 300 billion, 500 billion, 700 billion. So things are moving quite quickly. And it's important to understand what's really driving these costs, or what's really driving this market size and this growth. And it's really coming from two primary sources. And the first one here on the left is compute. And this is really one of the more underrated sources. Over the kind of past few years and even past decade, we can say compute has been getting bigger and faster. We've been getting more processing power, more memory, more storage, especially on the cloud where everything's kind of elastic and you can scale up quite quickly. And the other side that's more well-known and certainly gets a lot more media attention is the models, right? Every year, or it seems like every few months or every few weeks these days, we're getting new state-of-the-art models that are, getting better accuracy and they're much larger. They have billions of parameters. And this is happening in all kind of fields, whether it's computer vision, NLP, games, recommender systems, or what have you there. But the tricky part is that, this isn't all sunshine and rainbows. As everyone's kind of been chasing the latest and greatest, whether it's, bigger, faster, and stronger compute and models, costs have been going up dramatically. And this is especially true for deploying models on cloud platforms. Cloud is said to be elastic in the sense that we can easily scale up and down, but that also means it's easy for costs to spiral out of control quite quickly, right? Because if you're able to say, I want 5 servers, and quite easily you can switch to having 100, it's quite easy for things to spiral out of control cost-wise. And so, if we take a look at our kind of fun little equation here, if compute is getting bigger and that costs more, and models are getting bigger and those cost more, well, a little money bag here, which we can think of as kind of our profit or our revenue, is getting smaller and smaller. And so the $1 million question is quite literally, what can we do about it? How can we still get great performance out of our models while keeping our costs as low as possible and still delivering value at the same time, right? And that's really what this presentation is going to be about today. And we're going to touch upon 4 ways that we can leverage compute more intelligently, this kind of first primary source of these costs that have been going up, and 3 ways that we can leverage our models more intelligently. And by more intelligently, I really mean being smarter about how we are leveraging our compute in our models. And throughout the presentation, you'll see through the different methods the kind of specifics about that. And they're really quite practical and not too hard to execute. You just kind of have to know where to look. And we're going to start with our compute here. And the first method I'd like to introduce to you is choosing the right instance type. And the key thing to understand is that not all servers, whether they be CPU or GPU based, or whether they're on the cloud or on-prem, are going to be made equal. And on top of that, going more expensive does not necessarily mean you'll be getting linear gains in inference speed. And in this case, I've picked out here the K80, the V100, and the T4. The K80 here, it's got 12 gigabytes of VRAM, which is pretty good. The inference speed, what you'll find, and the training speed as well is kind of slow, especially in comparison to these other two. And the smallest server type that you can get on something like AWS is a P2X large, right? And this will cost you about 90 cents US per hour if you get this on demand. On the other hand, if you switch over to something like the V100 here, you'll be getting more memory. It's very fast in terms of inference speed. And the smallest instance you can get is P3.2X large, but it's going to cost you quite a lot of money, $3.06 an hour. Finally, we have in this last row, the T4, which is honestly one of my favorite here. The reason being is that if you were to test out the inference speed or the training speed here, you'll find that it's actually quite close to the V100, probably around 70 to 80% in most cases. But if we look at the smallest server type we can get here, which is the G4DN, and we look at the cost, it's about a sixth of the price of the V100 here, even though it's actually quite close in terms of speed. And that's really fantastic because it means that in a lot of cases when we're doing inference and you're deploying these machine learning models to production, you can quite easily switch over GPUs and save a ton of money, right? And still get a very similar overall throughput. You might need, a little bit more extra servers because it is a little bit slower, but overall you'll be saving a ton of money because it's a sixth of the cost. Now, if you do need the absolute peak inference speed, of course, the V100 is still probably going to be one of your best bets. But if you're okay with each kind of example or data point being processed that's slightly slower, but the overall kind of application being faster and much cheaper, then definitely the T4 is going to take you quite a long way. And at the end of the day, the best thing you can do here is to spin up one of each of these servers. And there are even others on AWS, other instances with GPUs, and just test the inference speed, right? Different models are going to behave differently, so your trade-offs are going to be a little bit different. So it's best to just run a quick benchmark, and you can often find yourself saving a lot of money through this with a pretty quick and easy test. The second method here for cost reduction, leveraging compute specifically, is to use spot instances. And spot instances, in a nutshell, are basically unused servers from the cloud providers. Now, they're going to be called different things, whether they be on, AWS or Azure. They'll be called spot instances. On Google Cloud, they call them preemptive instances. But essentially, they do the same thing, which is basically that these cloud providers have many extra servers, and not all of them get purchased or reserved all of the time, right? 100% of the time. And so what they do to at least get some money out of these is they put them up for auction. And the beauty of this is that the price of those servers are often a lot lower, even up to 90% lower than the on-demand price. And the price is simply determined by how many extra servers Amazon or Microsoft or Google or whatever your cloud provider is, how many of those extra servers they have at the time. And as you can see in this table, this was a snapshot I took about a week before this presentation, and of these GPU servers that we took out in the last slide. And here you can see the on-demand price versus the spot instance price, and it's about a third of the original on-demand cost, which is a massive, massive saving. Now, there are a couple of things you want to keep in mind with spot instances. They are the cloud's extra servers, right? And what that means is that if someone needs them and they decide to reserve them or to buy them at a higher price than your bid for the spot instances, then the cloud provider can take them back and shut them down at any time with about a 2-minute warning, essentially. That being said, it's not that frequent. I've had some servers that run for weeks straight, so you really won't have to worry about your servers going up and down super duper frequently. And what you really want to do in these cases is to use spot instances for situations where they make sense. For instance, batch processing or model training. If you think about, let's say, an application where you need real-time responses, having servers that can be taken away by the cloud provider is going to be a bit dangerous. But if you're doing something like batch processing, where the time that you need to deliver your results is not super critical, or if you're doing model training and you're able to save your checkpoints remotely for each epoch and say some remote storage like S3 or something like that, then spot instances fit perfectly and you can save a lot of money that way. And on top of that, what you can do, kind of a tip I have, is to always have some budget and some reserved or on-demand instances. And this way you can kind of strike a balance between, always having stable compute if your data science team or your ML research team needs to do, let's say, model training, or you just want to keep up with your processing. You'll always have that, but at the same time, you can save a lot of money when you don't necessarily need that 100% live computing power. The third method here for compute-based is asynchronous processing. And the most common and simplest way to set up a processing pipeline when it comes to machine learning is to do the processing all sequentially on the same server, basically. So if we take a look at our illustration here, for example, if we're trying to process this video, we're streaming in all these video frames, you would read and decode the first frame. And then once you're finished that, it would go to the pre-processing step. And then once it's finished that, it would go to the inference step where you run your model and perhaps that's being executed on the GPU. And then you might pass it to a post-processing step where you do some extra manipulation or perhaps some business logic. And the problem with this is that a lot of the time, doing this processing on one single input at a time doesn't take full advantage of all the computing power that you have on the server. And this is going to be the case whether you're running the model on CPU or GPU. It's just that you're waiting for each data point to be processed, and a lot of the time you can fit a lot more on that same server. So what we can do is kind of switch to asynchronous processing, where the idea is to have each and every step being executed in its own kind of separate process. So what we're going to be doing is constantly reading in these video frames, right? And we're going to be decoding them. And this pre-processing step is constantly going to be pulling these frames. Whenever there's a frame ready that's been read into memory, it's going to be constantly pulling it. On the other hand, this ML model here, as long as it has capacity to do so, it's going to be constantly pulling for the previous step, and so on and so forth, however many steps that you have. And really the main idea is to maximize the compute that you're using. If there's a certain process or you have some extra CPU power or GPU power, we should certainly be using it and trying to basically fill up the funnel at each different stage here, right? And kind of once again, similar to what I mentioned about the first point, which was the spot instances. The first one was choosing the right instance type. The best thing you can do is to do a benchmark, right? Put this up, do some testing, and see, how many data points you should be processing on the CPU at a time, or how many data points you should be processing on the GPU at a time. And then you can find out what's the optimal point where you're maxing your compute usage. And there's sort of two ways you can do this. You could do this on the code level where you're executing each step as a different process or a different thread, or this can be built out as a distributed system where you might have this running on a completely separate server as a separate microservice, for example. And then this step is running on a separate server, and perhaps the communication between them is some type of queuing system, or it could be like a Kafka topic, or like a pub sub model. But in any case, you can kind of distribute these processes as well. It does add a little bit of engineering overhead, but certainly you'll be able to optimize more, because then you can pick servers that are purely optimized for each step, right? You can pick one that's optimized for reading and decoding, pick one that's optimized for pre-processing, pick one that's optimized for GPU inference, etc. The last one here for leveraging compute more intelligently is inference batching. And on very similar lines to maxing out your servers that we kind of looked at the previous slide, it's the same sort of idea with inference batching. And a lot of the time, with these big servers, especially on the cloud, for both CPU and GPU, they have a lot of memory, and frankly, a lot more than you need. We looked at the V100 and the T4 earlier. They have 16 gigs of VRAM. And on top of that, the V100 actually has 61 gigabytes of regular RAM, right, of regular memory. And a typical CPU server can easily have a lot more. You could scale up to hundreds of gigabytes of RAM. And that basically means there's a lot more room to process data. And what you can do, instead of trying to process a single data point at a time here, you can try to essentially batch them together and run them in parallel. And the beauty of this is that modern libraries like TensorFlow and PyTorch support batch inference out of the box, right? All you have to do is stack your arrays together or your tensors, and they'll kind of automatically handle that for you, which is very convenient. And again, kind of the way you want to leverage this is by doing some testing and some benchmarking, because as you pass more and more data in a single batch, you actually run into a bit of a trade-off. You might be able to fit many data points in memory, but you might not have the actual compute power, whether it be on the CPU with your cores or on the GPU with your CUDA cores, to actually process those quickly. And so what you'll find is that sometimes when you use a huge batch size, it can fit into memory, but the inference speed on average per data point actually slows down. So what you want to do essentially is, for your particular model, give that a test. Just go up linearly, 1, 2, 3, 4, 5, etc. For your batch size, and see what the average inference speed is going to be, and then try and target that for your batching. And that's how you can kind of optimize the average inference speed and the cost there. That's about it for the methods where we can leverage compute more intelligently. And now we'll look at 3 methods that we can do kind of the same idea with our machine learning models themselves. And the first one here is to go data-centric. Now, if we think about it, there's really 2 options or 2 key ways to improve the accuracy or whatever machine learning metric that you're using. I'm going to use the term accuracy here just for simplification, but just know that these kind of ideas can apply to really any machine learning metric. And there's 2 kind of paths you can take for improving your metric. You can either go with the models or with the data. Now, for improving the models, you might do things like add more layers to your neural network, change your training scheme, or use some kind of new state-of-the-art technique. Now, the tricky part about this is that gains in state-of-the-art accuracy of models might be very fast from a research perspective, where we might be able to gain, say, 5% over a few years on some standardized benchmark, but actually quite slow from a business perspective. Waiting years for a few percentage points might not cut it, especially when you have, many customers and you're competing against so many competitors and things. That's a long time to be able to wait. And on top of that, doing such work is pretty hard. It's hard to build a new machine learning pipeline. And a lot of the time, these models are kind of just getting bigger and more complicated. And so they're using more memory. They're harder to optimize. They're much larger and slower, and really they're getting more expensive. So you end up trading off this cost for this accuracy or this machine learning metric. And it's kind of just a very complicated process. We could say in a nutshell, new models are hard and the gains are relatively small. On the other hand, getting new data is comparatively easier. It is time consuming, it's tedious, and certainly, a lot of data scientists or machine learning researchers are going to find it a little boring, but it is very straightforward and can often lead to multi-percentage gains. If we take a look at this table here, I borrowed this from a presentation made by Andrew Ng, who's kind of really pushing this data-centric movement. And basically they had 3 different models here, and this is their baseline accuracy. And it was for 3 different kind of applications, steel defect detection, solar panels, and surface inspection. And what they found was that by taking a model-centric approach, their gains were minimal to just nothing, really. But on the other hand, when they went with a data-centric approach where they just collected more data for their application or cleaned up their current data, they got massive gains, especially in comparison to the zeros you were getting here, or the very tiny numbers you were getting here with the model-centric approach. And the results are quite clear, right? Is that data-centric is simply comparatively easier, it's more reliable, and it's certainly a lot less risky. And it kind of comes with an added benefit as well, which is that you can often stick with an older, smaller, and faster model that performs fairly well on a benchmark and just focus on collecting more data and better data instead of using a bigger, slow model that might be the latest and greatest, but is a lot more expensive and more complicated to use. And this is going to be easier and faster to do, and your research teams don't have to spend time doing a lot of what's interesting research, but certainly quite risky from a business perspective. There are other ways that we can go data-centric. We can go beyond just collecting more data. We can also improve the usage of our current data. So, there are the classic kind of manual techniques of data augmentation, and there's new ones kind of coming out every day, and new techniques with synthetic data. There's also things like auto-augment, which are basically learned methods of augmentation, right, that you kind of apply during training. And those are very interesting. You can also, instead of trying to generate new data, try to use cleaner input data, right? Look through your data set and throw away anything that's heavily distorted, that doesn't fit your target, or in general, is just bad for training. I know that it's boring, but it's definitely worth it, especially when you have, if you're, let's say, trying to do sentiment analysis on some English text, and maybe you have like Spanish or Portuguese language text in there. That's certainly going to throw off your model training. So a lot of the time, it's a matter of kind of seeking out these sort of smaller data points and that are not really suited to your target, and kind of just removing those. At the same time, instead of cleaning your data, you can also try to get better data at the source. And that's basically by having better data input pipelines. If you're working with something like images, for example, try to improve the cameras, whether it be the quality, the FPS, etc. Or don't apply heavy compression to your images. Use PNG instead of JPEG type of image files. If you're working with tabular data, try to collect more of the features at the source. A lot of the time when users are entering, let's say, a form online, or perhaps you're collecting from some sensors or something, you're not collecting all the features that you need, or they're incomplete, or there's missing data. So you have to do some imputing where you're filling in these rows that are empty, or they have nulls, or anything along those lines. It's going to go a long way if you could just capture that information at the source, so you're not having to do this kind of artificial projection or filling in of your data. And this last one here is what I call filling in the gaps, or fill in the gaps. And I can give the example of if you're working with something like an object detection model for self-driving cars, and you find that, let's say, you don't have a lot of images in dark settings, or when the camera is blurry, or of certain street signs, for example, then focus on collecting more of those kinds of data. You're filling in these gaps where you're finding, okay, there's a gap in my data set, whether it be a certain class or a certain setting or condition. You want to fill those in. And a lot of the time, your lack of accuracy or lack of high machine learning metric is coming primarily from those really weak kind of classes or data points or what have you. And so filling in the gaps is really going to boost the performance quite a long way. The second method here, which is one of my favorites, is to use more models, not better ones. And what do I mean by that? The most common way of trying to improve model accuracy is to do things like add more layers, adjust hyperparameters, or look for the latest and greatest state-of-the-art technique. But there's a more efficient way of doing this by just using more models, and it's a lot simpler. So you can go with using model ensembles, and that could be based on optimizing each model for a different metric, maybe one for precision, one for recall, and perhaps you want to optimize your F1 score at the end, right, which kind of combines precision and recall. You can train each model on different cuts of your data, right, traditionally kind of known as bagging, and then just merge the results at the end, right, average the resulting probabilities or predictions if you're doing a regression or what have you. And oftentimes you can use a few or even several good models in your ensemble, and they'll get higher accuracy at a lower runtime than one big state-of-the-art model. And this is just a function of the fact that if you look at our state-of-the-art right now, what you'll find is that these huge models, right, they're getting like maybe a couple or a few percentage points at best more than these substantially smaller models, right, that are much, much faster. And so combining a few of them, you can get away with that speed-wise and save quite a lot of money versus using this huge state-of-the-art model. Another method of ensembling that's actually used a lot in research competitions, but not so much in production settings, unfortunately, even though it's a great technique, is called test time augmentation. And let's say you're doing an image recognition problem, you can run the same model on multiple versions of the same image. So you can flip it, rotate it slightly, perhaps change the lighting a bit, and just run the same model, the same inference on that kind of warped or slightly modified input image, and then just average the results at the end. And this is often enough to squeeze a couple of extra percentage points out of the model. It's very standard practice in these kind of large image recognition or object detection kind of challenges. So definitely a good technique to try. And the second part is to fine-tune your models for specific situations. Now, what do I mean by this? Let's say you're running a model to determine what sales to show your various customers on your e-commerce website. Well, instead of having one huge model run everywhere, let's say in every region, every country, every store, or for literally every single customer, you can fine-tune a smaller model for each different country or each different region. And since the model is fine-tuned on data that's specific to that region, you'll actually be able to get a much higher accuracy than normal. In a way, you are, dare I say it, overfitting on that specific use case just a little bit. But the beauty of this is that because that data is kind of centralized to that specific region in the country or has certain biases, you can get away with doing that, right? And you can basically have a bunch of small models rather than one big generalized one that kind of just works okay, on all of them, kind of a jack of all trades, master of none in a way. And at the same time, this effectively transforms the problem from research to engineering, which is actually a lot easier to solve. So instead of trying to break the state of the art, we just have to figure out how to deploy a lot of models. Now, this is not easy per se, but it's easier than trying to do, really kind of complicated or risky breakthrough science. And kind of coincidentally, about a week ago, before my presentation, I was preparing these slides, Google actually released a blog post and a related research paper called Model Ensembles Are Faster Than You Think. And they essentially published some really great results on model ensembles versus having one huge model. And they showed two techniques. One of them is traditional ensembling, where you have two different models here, and you average the prediction at the end. The other one is called cascading, which is also used by some organizations, where you'll basically run your first model here, and you'll say, okay, did I get a high confidence, right, or a very high probability? And if the answer is yes, then it's an easy data point or an easy example, and we take that prediction. If not, then we're going to run our ensemble and our second model, and then we'll average the prediction because we think perhaps it's a bit more challenging. And what they found is basically that in doing this, ensembles and cascades get consistently better accuracy numbers or better results. Here's the top one accuracy on ImageNet here. And as we go to the upper left, the ensemble models are better than the baseline, and so are the cascade models, in fact. And they're getting less flops, so less floating point operations, basically making them run faster because you're able to use a couple of smaller models versus one bigger one. And the last method we'll look here at kind of two different flavors, which is model optimization. And the first one here is quantization. If you actually look into TensorFlow and PyTorch, what you'll find is that when you train a model in those libraries, the default data type is floating point 32, which works great for training, but oftentimes you don't actually need that high of a precision to get great accuracy and business value out of that machine learning model. You can use floating point 16, in which case the model is going to be about half the size, and you'll be getting a speed up of 1.2x to 1.8x. And most research results show an accuracy loss of less than 1%, which is quite acceptable in a lot of cases. And if you think about this, this is really the upper bound in the vast majority of cases here, this 1%. A lot of the time, it's much lower, maybe 0.5% or 0.1%. And sometimes you even get lucky and the accuracy kind of goes up. Neural networks are kind of very wild beasts. So, a lot of different things can happen, but generally speaking, you lose just a touch of accuracy, which might be acceptable for the business use case, especially if you're kind of combine this with different methods to increase your performance, like ensembling or going data-centric and that kind of a thing. And you're getting great speed ups too, which of course translates to cost reduction at the end of the day. On the other side, you can use integer 8 quantization level, which is going to make your model a quarter of the size and at the same time get you much higher speed up on average, but you're taking a bit more of an accuracy loss here. Now, this may or may not be acceptable. At the end of the day, I always recommend, again, kind of do a benchmark on your data set. Sometimes it'll be a lot lower than 5%. Sometimes it's less than 1%, and it's perfectly fine. Other times it's 3, 4, or 5%. And the best thing you can always do is run a benchmark on your test data set and see, where it kind of falls and what's acceptable for you. But it's always very easy to do these things quickly, and you might end up making, kind of a massive speed up out of this. And just to kind of make you aware of something as well is that there are techniques that actually combine floating point 16 and int8 quantizations. And the idea being that, use floating point 16 where we think that it's a little more sensitive, where accuracy might drop a little more, and use int8 where we're a bit more flexible. And so you're able to kind of strike a balance between these two rows essentially in this chart. The second method of model optimization is called pruning. And the idea is essentially that we can remove some of the parameters of a model without having a significant negative effect on the performance. And so there are many methods of doing this. Some techniques just remove weights, as I've kind of done here in this illustration. Some of them drop entire neurons here, right? But in general, there's other techniques too. At the end of the day, it's all about reducing the model size by removing some parts of it, right? And you can get some pretty good speed versus accuracy trade-offs on your model using this method. There was this great paper recently called "What is the State of Neural Network Pruning?" And they essentially ran this massive benchmark on all these different pruning techniques. They had, lots of fancy tables and charts and results and numbers and things. I've basically summarized it in this table right here. And you can kind of see a clear trend of, as you're willing to drop off more accuracy, so you're pruning more aggressively, you can compress your model a lot more, right? So you're taking away a lot more of it, so you can fit a lot more data points into memory. And you're getting a massive speed up, that kind of goes up, but you're going to be dropping more and more accuracy. And very similar to the quantization technique is that do a benchmark and kind of see what you get out of it. Some of the time you'll drop, virtually nothing or very, very little. And again, you can kind of mitigate this by trying to do, let's say, maybe you want to try dropping off 5 to 10% accuracy, in which case your model is going to be substantially faster, but maybe you use like a huge ensemble, or you add more data, or you do a lot of fine tuning or something along those lines. So these are all going to vary based on your application. And again, kind of the best thing to do is to run this benchmark and kind of see where the trade-offs are, right? And you can find yourself saving quite a lot here with model pruning and for model quantization. I know I'm running low on time here. I will just do a very quick summary, which is essentially this chart here. We looked at 4 methods of reducing costs via leveraging compute more intelligently, which was selecting the right instance type, just doing a quick benchmark, putting up various server types and seeing what the average inference speed is on each one. Spot instances, which are great for situations where you're doing batch inference or model training. Asynchronous processing, which we can do at the code level or as a distributed system, constantly running things in each process. Batch processing, where we're essentially processing multiple data points at the same time. That's the compute side. On the model side, we saw going data-centric, and that can be done by either collecting more data or using cleaner data by improving your data pipelines or kind of culling through your current data set and cleaning that up. You can use more models instead of bigger ones, whether it be via ensembles, test time augmentation, or various other techniques such as fine tuning for specific situations, effectively transforming it from research to engineering, which is a lot less risky. And lastly, optimizing your models, which is going to be primarily quantization and model pruning. That's about the end of the show, and I hope you enjoyed. I hope you learned something new, and I'd be happy to take any questions that you might have now.
So the first question is from David. David asks, curious as to a case study where you applied these methodologies and the cost breakdown. What overall savings were you able to achieve?
Right, fantastic question. So let me kind of go back here in several slides. I've actually in production used choosing the right instance type. At my previous company, Indus.ai, we switched over from the V100 to the T4. And for us, the inference speed was perfectly fine. So we were able to save, 60, 70% here. We were doing a lot of batch processing, so we combined spot instances, and this worked perfectly fine for us. And we did this technique here, this tip I have, which was to keep some reserve instances handy. We did a bit of asynchronous processing where kind of applicable. We did batch. So I've essentially tried all of these. I think this sort of targets your question a little more. If you were looking for something to start with, I would certainly start with choosing the right server type. I think it's very easy to try at first. It's relatively low cost. I mean, you kind of put it up and run the inference. You're not going to drop any accuracy. You don't have to worry about managing spot instances. So I always recommend this one first. It's going to depend on your specific situation, but I've definitely had experience with all of them one way or another. And a lot of the time you can get very acceptable and worthwhile trade-offs, essentially. No problem.
Thank you, George. Hope it answers your question, David. So the next question we have is from China Hope. Are there specific designs that lend themselves to some techniques more than others?
Are there specific designs that lend themselves techniques more than others? Designs in terms of what? Are you talking about perhaps the machine learning application of the model, or more so the infrastructure kind of design? I think certainly, I mean, I can touch upon the fact that, with models. I think it's a bit tricky to say in terms of what lends itself more so to another. And that's really why I stressed benchmarking. Yes, essentially, because neural networks are kind of such a beast. I think there are some researchers and things that publish papers and they say, you know, maybe this technique works more so in this situation than in others, but in practice, and in my experience, it's really been the best thing you can do to guarantee and to basically sleep well at night is to run your own benchmarks on your specific situation. And as I mentioned, they're really not difficult to do. If we're talking about models, you can go down here. TensorFlow, for example, has a model optimization toolkit that does this optimization and this quantization and pruning out of the box. So definitely worth a try.
So thank you, George. Hope that answers your question, Dina. The next question is from Rajiv Abraham. What is your benchmarking framework process that makes it easy for you to test different model combinations on different machines on the cloud? For example, do you use Locust or even testing different models?
As far as testing methodology for different inference speeds, I wouldn't say I've done anything too complicated. I think that once your models are containerized, the kind of standard cloud servers, especially since they have things like CUDA or what's it called, the graphics drivers installed already, the NVIDIA drivers, it's very easy to kind of pull that down to the server once you have it up and just test your inference speed. As long as you have a standardized data set, you can use the test data sets or the validation data set that you were using to train your model anyway, because that's going to be reflective of the task you're trying to target anyways. So yeah, in terms of making it, I guess, scalable for testing, really just a matter of using standard, I guess, software engineering best practices, we can say.
Thank you, George. And it looks like we are running out of time now. So thank you for your talk on reducing costs by leveraging the right compute and model methods. And I'm sure we all learned a lot from this session. Thank you to the attendees. If you have any further questions for George, please feel free to reach out to him on the Vova app. And also, please feel free to check out the Vova app for community networking, meetups, and job boards. Thank you so much, everyone.
Yep, thanks everyone. Feel free to message me on Wova, LinkedIn, anything like that. If you have any further questions, I know we had a short question session here today, so anytime here and available. And thank you very much for attending.